Hydatellaceae is a family of plants that, until perhaps 2 or 3 decades ago, botanists believed were a kind of grass. Only now do we know that they are most closely related to some of the earliest diverging flowers, the nymphaeales, alongside the water lilies. And, can you really blame them? Look how closely it resembles grasses in the genus Centrolepis, which it was once categorized with. This ancient flower managed to fly under our noses for more than a century of literature after its discovery. Please, if you have a few minutes, I implore you to stay and listen to Flowers of the World, Part 2, Hydatellaceae. Our story begins nearly 200 years ago, August 1840. It is almost springtime on Van Diemen's Land, an island we now know as Tasmania. The Ross expedition is preparing to sail for the South Pole. Of the 128-man crew, 23-year-old botanist Joseph Dalton Hooker is the youngest. Having set sail nearly a year ago from the Chatham dockyard in Kent, Hooker has dutifully collected and documented plant specimens at each step of the journey so far, from the Cape Verde archipelago of West Africa to Trinidad, east of Brazil, and the Cape of Good Hope in South Africa. Over the next few months before their departure, Hooker will come to befriend one Ronald Campbell Gunn, an eminent Tasmanian botanist. Hooker writes, "There are few Tasmanian plants that Mr. Gunn has not seen alive, noted their habits in a living state, and collected large suites of specimens with singular tact and judgment." Among Gunn's vast collection, some of which he donated to Hooker to take back to England, is an inconspicuous aquatic plant. Gunn shows Hooker some of these plants growing in freshwater puddles and tells him how, when it fruits later in the year, the flowers will fill the shallow pools with tiny bright red stars. 3 months later, Hooker will continue with the rest of the Ross expedition further south, where they will encounter the sheer walls of the Ross ice shelf, halting their progress. The expedition would continue to sail around Antarctica for another 2 years before returning to England in 1843. Back in England, Hooker compiles his findings on his expedition into 4 parts, the last of which, published in 1858 in 2 volumes, was on the Flora of Tasmania. And in the second volume of this Flora Tasmaniae, Hooker presents the first valid publication of the plant shown to him by Gunn. He calls it Trithera submersa, Trithera meaning 3-windowed in Greek, referring to the way the fruit splits along 3 ribs to release the seed within. In a few paragraphs, he gives a brief description and color illustration of the plant, the first of its kind. Now, I would be remiss to not mention the contribution of Ferdinand von Muller, government botanist for Victoria, who technically published on Trithera 10 years earlier and named it Gensella tasmanica, after the grasses of genus Juncus. However, Muller did not give a description nor a type specimen for his publication, necessary material for a valid publication, rendering his name a nomen nudus, or naked name, and thereby illegitimate. Hooker himself mentions Muller's publication in Flora Tasmaniae, and did not choose to keep the name Gensella, as he didn't think the plant resembled genus, and it wasn't confined to Tasmania. To Muller's credit, he is responsible for the early placement of Trithera in the now obsolete family of grasses Centrolipidaceae, where it remained for over a century. By the way, I found one of Muller's letters where he's clearly salty about this. Here he's writing about the Areocoliae, and just has to mention his feelings about Hooker's Trithera. a name he is, quote, happy to adopt, but for his own vindication wants to remind Dr. Hooker that Lamarck employs the term Johnsonelle for a closely related genus. So, Lamarck sure seems to think that Trithura resembles genus, doesn't he, Dr. Hooker? Furthermore, he says he was thinking particularly of the species Genus capitatus in his choice of name, a plant published decades ago, which must have just slipped the notice of the good Dr. Hooker. Anyhow, the name Hydatellaceae did not appear until 1904, when German botanists Ludwig Diels and Ernst Pritzel published the species Hydatellaceae australis from a type specimen collected in Western Australia. Hydatellaceae coming from the Greek hydatos, meaning of the water. By this time, a few more species of Trithura had been described. T. occidentalis by Bentham in 1878, T. filamentosa by Rodway in 1898, and in a few years, T. inconspicua would be published by Cheeseman in 1906. Botanists noted the two genera must be close cousins, and in 1906, close examination resulted in the defining of Trithura as those plants with dehiscent fruit, that is, the ones that would split open into three parts to release the seed, as in T. submersa, and Hydatellaceae as those plants with indehiscent fruits, as in H. australis. By this definition, T. filamentosa and T. inconspicua, both perennial plants with indehiscent fruits, were transferred to the genus Hydatellaceae. By this point, Trithura and Hydatellaceae had been placed in the grass family Centrolipidaceae by Ferdinand Muller's precedent, and were grouped together in a tribe called Trithuriae. This placement, however, was starting to strain the way the family was defined, as mounting evidence started to show something was deeply wrong. All the way back in 1858, in Hooker's first publication of T. submersa, he had already noted two significant differences between Trithuriae and the other Centrolipidaceae. First, whereas Trithura capsules open by 3 slits, dehiscent Centrolipidaceae fruits open by a single longitudinal slit. Second, the anthers of Trithura are dithecal and base-affixed, whereas those of Centrolipidaceae are monothecal and versatile. Furthermore, his observation that Trithuriae form an involucre reveals another difference. Whereas grasses have inflorescence called spikelets, where each flower is sandwiched by bracts or floral leaves, each of Trithuria's bracts do not support flowers, instead forming an involucre at the base of the inflorescences. These differences might seem minor, but whereas Centrolipidaceae's features are typical of graminoid or grass-like plants, Trithuria's floral features are a hard departure from other grasses. Usually, these embryological features that have to do with flowers and seeds remain very similar among related plants, while size, structure, and habits can differ greatly. The fact that this is the opposite case here indicates some seriously divergent lineages between these two tribes. By the time of Diels and Pritzel's publication in 1904, already they write, quote, "There are such considerable differences in flower morphology between the two subgroups of this difficult family that at present there seems to exist no bridge between them." Despite this, it would take until Ulrich Hamann's paper in 1976 to compile all the evidence to properly separate Trithura and Hydatellaceae into their own family, Hydatellaceae, the family this video is about. By then, surprising microscopic differences had been discovered that suggested Hydatellaceae's primitiveness compared to the graminids. I will describe two in detail here. First, in the shape of the stomata, the pores in the surface of plants used for gas exchange. Centrolipidaceae has the typical parasitic graminoid stomata, with dumbbell-shaped guard cells and two small parallel subsidiary cells on either side. Hydatellaceae instead has primitive anomocytic stomata without any specialized subsidiary cells surrounding the simple round guard cells. Second, the pollen anatomy of Hydatellaceae was remarkably unusual as well. For some context, pollen grains often have apertures, places where the pollen wall thins or splits, where the pollen tube may grow out of the pollen grain and deposit sperm into the ovary. Grasses typically have monoulcerate pollen, with a single small round aperture called an ulcus at the end. Hydatellaceae has monosulcate pollen, with a single long aperture called a sulcus at the end instead, making the pollen somewhat boat-shaped. Again, a very primitive feature. These features and several others are shared by many primitive flowers in the Nymphaeales, but despite this evidence, placing Hydatellaceae with the Nymphaeales was not considered until 2007, when Canadian researcher Jeffrey Sarala and his colleagues utilized modern advancements in molecular genetics to conclusively place it with the Nymphaeales. How did this happen? How did this error remain uncorrected for so long? The answer is, in a word, scope. There are a lot of flowers out there. Over 400,000 species, distributed into 416 families as of the APG4. That's about 1,000 species per family. You could spend a lifetime studying just one such family, and some people have. The phylogeny of flowering plants is a ridiculously massive body of knowledge, and in these cases, any single person touching it naturally tries to be conservative in their meddling. You might see a piece clearly out of place, like Hydatellaceae, but without complete knowledge of the whole structure, you would caution to maintain your search to the immediate surroundings, so as not to disturb what you do not know. Usually, this works well. Our predecessors were smart people, even if they didn't have the technology or knowledge we do now, and they usually put things in roughly the right spots. Sometimes, though, there exists a difficult error that takes the work of a whole team of people searching a whole lot of space in detail to find the proper correction. In this case, it took Sarala's team of 8 authors performing a multi-gene molecular analysis of all families in the order Poales to correctly deduce the exact nature of this oddity. To round out our history, I want to quickly bring us up to speed on the present state of Hydatellaceae by reviewing all the discoveries and changes I missed earlier. In 1981, Australian botanist David Allen Cook published Tritheria lanterna, found in northern Australia, the first tropical member identified. In 1983, Cook was able to formally describe 2 more species, Hydatellaceae dioecious and Tritheria bibracteata, from a proposal first made by Kew botanist Otto Staff in 1903, while analyzing material from Western Australia. The next discovery might be quite a surprise. Let's leave Australia behind for a moment and jump to the Western Ghats of India. The year is 1994. Goa University botanists Yadav and Janarthanam are connecting specimens in the remote forests of the Sindhuburg district of Maharashtra, where they come across a plant they can't seem to identify. They first think it might be some sort of moss, but noticing the flowers, realize otherwise and consult the literature. In their search, they are able to find Cook's publications, without which they may not have known of Hydatellaceae, as in their paper they seem to only be aware of the 3 species published by Cook just 10 years prior. With this knowledge, they can place their specimen and name the species Tritheria concanesis. The implications of this find are extraordinary. The last time India and Australia were a part of the same landmass was over 100 million years ago, when the supercontinent Gondwana was breaking up in the early Cretaceous period. This would also be the time that the first flowers were beginning to evolve. Could the fact that these 2 populations of Tritheria, separated by 7,000 kilometers and 100 million years, still resemble each other so closely, indicate that they are much unchanged from the very first flowers of the early Cretaceous. It's a real possibility, but lacking solid fossil evidence, we are more confident on those features shared by all early diverging flowers, such as vesselousness, monosulcate pollen, and anomocytic stomata, than we are of the overall structure and habit of the early flowering plants. After all, the first flowers may have perhaps resembled the woody shrub Umbrella instead, which I covered in my last video. To finish catching up on our history, I must mention the work of Sokoloff and colleagues, from which I have drawn a tremendous amount for this video. In 2008, Sokoloff was able to show specimens of H. dioica were actually male individuals of the same species as T. occidentalis. Furthermore, they showed that T. occidentalis had unique traits that could be distinguished from all other species of Trithura and Hydatellaceae. Thus, the two genera did not represent natural groups, and were merged, leaving Hydatellaceae a monotypic family with only the genus Trithura. Finally, Sokoloff was able to describe 4 new species of Trithura: T. austinensis, T. cookiana, T. polybracteata, and T. cowiana. The last update I need to mention is Trithura fitzgeraldi, published also by Sokoloff in 2019. And with that, we are finally caught up with the 13 species we know about today. Today, Hydatellaceae remains a peculiar family of inconspicuous plants. Growing in small puddles formed from old footsteps and tire treads, its ancient lineage and place among the earliest diverging flowers could almost be overlooked, and was for over a century. In recent years, it's finally earned its place in culture. Trithura inconspicua, for example, was voted New Zealand's favorite plant in 2024, and conservation efforts have mounted in the nation to protect it from extinction. It's a reminder that sometimes all you need to do is look a little closer. Thanks for watching. I hope you enjoyed that, and I'm sorry each one of these takes so long to make. Please consider subscribing so you don't miss me next time when I talk about K. bombaceae, or the water shields.